NASA just confirmed that Earth will have what's being called a second moon until 2083. But here's the twist that changes everything about this story. This isn't actually a moon at all, and the truth behind these celestial visitors reveals something far more fascinating about our cosmic neighborhood than any clickbait headline could capture. Let me cut through the social media hype and explain what's really happening in space above us. The object everyone's calling Earth's second moon is actually a quasi-satellite named 2025 PN7, roughly the size of a small office building at just 19 meters across. Unlike our real moon, which faithfully orbits Earth every 29 days, this tiny asteroid follows its own path around the sun while appearing to dance alongside our planet for decades at a time. To understand why this matters, we need to grasp the crucial difference between true moons, quasi-moons, and mini-moons. A true moon like ours is gravitationally bound to its planet, locked in orbital embrace. But 2025 PN7 and objects like it are cosmic hitchhikers, following Earth-like solar orbits that keep them in our general neighborhood without ever truly belonging to us. Carlos de la Fuente Marcos from Universidad Complutense de Madrid perfectly captures this relationship when he says that if a true satellite is like a customer buying goods inside a store, objects like 2024 PT5 are window shoppers. They're browsers in the cosmic marketplace, interested but not committed. The story gets more intriguing when we examine 2025 PN7's timeline. This asteroid didn't just randomly appear in our vicinity. NASA confirms it shifted into its quasi-moon orbit in 1957, just in time to witness the launch of Sputnik 1, Earth's first artificial satellite. For the past 70 years, it's been our silent companion, maintaining distances between 4 million and 17 million kilometers from Earth. That's roughly 10 to 40 times farther than our moon, explaining why most people have never noticed this cosmic neighbor. But 2025 PN7 isn't alone in this celestial ballet. Earth regularly attracts these temporary companions, and recently we witnessed something even more dramatic. In September 2024, our planet captured an actual mini-moon called 2024 PT5, an asteroid about the size of a school bus that genuinely orbited Earth for 56 days before breaking free in November. Unlike quasi-moons, mini-moons are temporarily captured by Earth's gravity, becoming true satellites for brief periods. Paul Chodas, manager of NASA's Center for Near-Earth Object Studies, describes these encounters perfectly when he says this small asteroid is caught in a little dance with Earth. For 2 months, 2024 PT5 performed this dance at a distance of 1.5 million kilometers, about 4 times farther than our moon. The discovery of these objects represents a revolution in astronomical detection capabilities. MIT astronomer Richard Binzel explains that these happen with some frequency, but we rarely see them because they're very small and very hard to detect. Only recently has our survey capability reached the point of spotting them routinely. This technological advancement has revealed something extraordinary about these visiting asteroids. In January 2025, scientists confirmed that 2024 PT5 isn't just any space rock. It's actually a piece of our own moon, blasted into space by an ancient asteroid impact and now returning to visit its birthplace. Dr. Teddy Carita from Lowell Observatory led the research that cracked this cosmic mystery, saying they had a general idea that this asteroid may have come from the moon, but the smoking gun was when they found out that it was rich in silicate minerals, not the kind that are seen on asteroids, but those that have been found in lunar rock samples. This discovery transforms our understanding of the space around Earth. These aren't random visitors, but often fragments of our own cosmic history, pieces of the moon returning home after journeys lasting thousands or millions of years. The implications stretch far beyond academic curiosity. Consider Kamo-Oalewa, perhaps the most famous of Earth's quasi-moons. This 40 to 100 meter asteroid has maintained its relationship with Earth for decades, staying between 38 and 100 lunar distances away while spinning rapidly every 28 minutes. Like 2024 PT5, Kamo-Oalewa appears to be lunar material, possibly ejected when an asteroid created the moon's Giordano Bruno crater between 1 and 10 million years ago. The Chinese space program has taken notice. Their Tianwen-2 mission, launched in May 2025, is currently racing toward Kamo-Oalewa to collect samples and return them to Earth by 2027. At over 43 million kilometers from Earth and climbing, this spacecraft represents humanity's first attempt to bring back material from a quasi-moon. It's poetic justice, collecting pieces of our moon that have been wandering the solar system for eons. But why should we care about these cosmic window shoppers? The answer lies in their accessibility and scientific value. Unlike traditional asteroids that zip past Earth at breakneck speeds, Quasi-moons and mini-moons move in predictable patterns that make them ideal targets for future missions. Carlos de la Fuente Marcos notes that these asteroids are relatively easy to access for unmanned missions and can be used to test planetary exploration technologies with a relatively modest investment. They're natural laboratories for testing asteroid mining technology, spacecraft navigation systems, and planetary defense strategies. As one researcher put it, the second moon offers a great opportunity to test technology that mines asteroids for rare metals and minerals because it's easier to get the robotic technology on an asteroid that isn't hurtling away from us. The history of these discoveries reads like a cosmic detective story. The first confirmed mini-moon, 2006 RH120, sparked controversy when scientists initially thought it might be space junk from a Saturn V rocket due to its unusual spectrum. It took careful analysis to confirm this school bus-sized object was indeed a natural asteroid that orbited Earth for 12 months before departing in 2007. 2020, CD3 followed a similar pattern, captured around 2016 and escaping in May 2020 after astronomers at Mount Lemmon Observatory spotted it during its final approach. Each discovery refined our understanding of these temporary captures and improved our ability to predict future encounters. The detection technology continues advancing at a rapid pace. The Asteroid Terrestrial Impact Last Alert System, or ATLAS, represents NASA's cutting-edge approach to monitoring near-Earth objects. This network spotted 2024 PT5 using instruments in South Africa, while the Pan-STARRS Observatory in Hawaii discovered 2025 PN7. These systems scan the sky continuously, building catalogs of objects that might pose threats or offer opportunities for exploration. So far, astronomers have confirmed only 8 quasi-moons total, making each discovery valuable for understanding how asteroids move and how Earth's gravity shapes the space around us. Each follows its own unique orbital dance, some staying close for decades while others drift away after brief encounters. The predictive power of modern astronomy means we can forecast these relationships far into the future. 2024 PT5, currently on its way back to independent solar orbit, will approach Earth again in 2055 and become a mini-moon once more in 2084 for about 43 days. 2025 and 7 will continue its quasi-moon relationship until around 2083 before finally drifting away into deep space. But the most fascinating aspect of this story is what it reveals about Earth's extended gravitational influence. Our planet doesn't just capture passing asteroids randomly, it participates in a complex gravitational ecosystem that includes a previously unknown population of lunar fragments called the Arjuna asteroid belt. Named after the mythological archer who never missed his target, Arjuna asteroids follow Earth-like solar orbits with low inclination and eccentricity. Many appear to be moon fragments launched into space by ancient impacts, creating a scattered trail of lunar material that occasionally returns to visit its origin. As researchers noted, the fact that 3 of these objects have surface properties compatible with lunar material suggests that asteroidal impact on the moon are contributing to the population of the Arjuna belt. And this is an unexpected and important result. This discovery fundamentally changes our understanding of the Earth-Moon system. Rather than existing in isolation, our planet and its satellite participate in a dynamic exchange of material across millions of years. Impacts blast lunar fragments into space, where they follow complex orbital paths before occasionally returning as mini-moons or settling into quasi-moon relationships. The implications extend to planetary defense and resource utilization. Understanding how these objects move helps us predict potentially dangerous asteroid approaches while identifying candidates for future mining operations. Their composition offers clues about lunar geology and the early history of impacts in our solar system. Looking ahead, the detection of these objects will only improve. Richard Binzel emphasizes that temporary captures are natural cosmic laboratories that help us understand the small bodies that come close to Earth and could be important for future space missions. As China's Tianwen-2 mission approaches Kamo-Oalewa and returns the first samples from a quasi-moon, we'll gain unprecedented insight into these cosmic relationships. The data will help us understand not just where these objects come from, but how they might serve humanity's expansion into the solar system. So while Earth doesn't truly have a second moon in the traditional sense, we do have something arguably more interesting: a dynamic ecosystem of temporary companions, lunar fragments, and gravitational dancers that reveal the hidden complexity of our cosmic neighborhood. 2025 PN7 isn't just a space rock tagging along for the ride, it's a 19-meter ambassador from the broader solar system, demonstrating that Earth's influence extends far beyond our atmosphere into the realm of asteroids, quasi-moons, and the scattered debris of ancient cosmic collisions. The next time you look up at the moon, remember that pieces of it are wandering the solar system right now, and some of them occasionally come home to dance in Earth's gravitational embrace before continuing their eternal journey through space. In a universe that often seems vast and disconnected, these cosmic visitors remind us that even in space, everything is connected through the invisible threads of gravity and the shared history of our solar system.